Is this thing on? Yeah, there we go. Hey, good evening, everybody. My name is John Ramey. I'm one of the organizers for the Austin Deep Learning Meetup. Hopefully you're in the right spot. Can everybody hear me okay with the mic? Okay, excellent. Thanks to Capital Factory for making this thing happen and dealing with a lot of our demands. Can you please turn off the AC with a broom? I appreciate it, man. So want to give a shout out to Novi Labs, my employer. Novi Labs, we're a startup and we are a machine learning company. We actually do that for real. We have a lot of job openings available right now, both full stack, front end lead, and machine learning engineer. So when I say machine learning engineer, I mean machine learning for real. So tomorrow when you go work on Tableau and you're doing your SQL queries, I want you to think about my team, because we are actually doing machine learning and deploying, and that's what our company does, and we do it fairly well. Please reach out to me, and I'll point you to wherever you can post your resume, et cetera. I want to give a shout out to the two guys who are about to give the presentation, the talk. It was last minute, and it's my fault. So they've scrambled and thrown together some slides. So if it's terrible, it's my fault, and if it's a good talk, it's my fault. So I'll take credit for that. Lastly, I sent out a request for presentations a week and a half ago. I was overwhelmed with really high quality talks, ideas. So of course we have Daniel and John who were gracious enough to volunteer this evening. I have not finalized March and April, so I have some pretty good, there's been some pretty good talks that were proposed, just got to get those ironed out. I'm going to be selfish for once. I'm actually going to give a talk probably in April. I've been looking forward to doing this one for a while, so I'm going to squeeze myself into this one. I'm going to be giving a talk on TensorFlow.js. I've been doing a lot of work with TensorFlow.js. So look forward to that. And if I have to bump it back to May so other people can fit in, it sounds great. But I want to give this call for talks again, not just online with my spammy emails, but also please see me after if you'd like to give a talk. Not only do we want you to give a presentation over something that you may have learned, or a blog post you've read, a paper you've read, et cetera. What we'd really like to see is code, right? So in the past, we had too many speakers not talk about code enough. And so that's what I've been urging a lot of our speakers to really focus on code. What does it mean to train this thing? What does it mean to deploy this thing? What does it mean to feed data through the entire pipeline? That maybe means for raw data all the way through, say, prediction or classification or whatever. So without further ado, I'm going to stop talking, and we're going to turn it over to Daniel Diamant and John Sigmund.
Thanks, John. My name is John. This is Daniel. Hold on. Hang on. And thanks for the warm introduction. Can everybody hear me okay? Yeah, okay. Too loud? No? Okay. As the title slide says, we're going to talk about a work project we did today. It's automated voice recognition. And we work for a company called Asteroid Technologies. We work on making AR tools easier for developers to make AR software. So it's a work project, so I have to open up the website here. So we have we're based in San Francisco, and so here's our website if you want to come check it out. A little icon there. So our main product right now is basically an IDE that allows you to build apps for ARKit, which is for iOS. So you use logic blocks and you drag and drop ML models and 3D graphics basically into the IDE, and you chain them together, and you can export it directly into Xcode, and it compiles into a project for ARKit. So we were tasked with building an automated voice recognition system for this application. So we had some tight deadlines and limited resources. So for training the model, we chose an open source TensorFlow implementation. So all the training code is open source. It's available, and there's a link in here that we'll show. And then they also provide code for exporting the model. But as all this is Mac, we can't export TensorFlow stuff. It's all got to be in Swift and CoreML, which is Apple's primary programming language and their representation for neural networks and ML models. So basically, the first half of the presentation, we're going to talk about how the model works, kind of how we went through the process of writing the code, and then the second half, we're going to talk about some of the software tools that we use to make that work. So the project itself covered a lot of ground, so hopefully that's the best fit for what people want to hear about. If you have more questions on a certain topic while we're going, just feel free to raise your hands. If we get tight on time, then we'll skip some questions and take them all at the end. First, kind of how the data flows through the model. So the model itself actually takes in a WAV file. It decodes that into a one-dimensional array of audio data. It takes that audio data and turns it into a 2D representation called a spectrogram. It takes the spectrogram, turns it into a 2D representation called an MFCC, and then we feed that into a convolutional neural network, which spits out a prediction. So we're going to go in depth into some more of that in a second, but this is just kind of the basic idea for how data is flowing into this model and coming out the other side. So the workflow is training is all done in TensorFlow, like I said. We had to do a few minor modifications to that open source code, but nothing serious, luckily. So once we're done training in TensorFlow, the tricky part is the TensorFlow graph actually has all of the audio processing stuff as TensorFlow nodes, and when you convert that to CoreML, it just doesn't work. So the only thing you can really convert between all the different neural network libraries is really basic layers. So your basic convolutional layers, I think basic RNNs, I think a few LSTMs, but once you start getting like recurrent loops and you start getting fancy stuff in there, all the conversion tools that are out there now pretty much don't work. So we had to take the TensorFlow graph, split it up, extract the CNN, convert to CoreML. I found CoreML a little ungainly to work with, so we have that in another Swift wrapper. And then at the same time, the pre-processing is done in C and Swift, and then they're merged together at the end to make the final product. Does that make sense so far? Kind of high level? And we'll talk about this in more detail. Okay. So then this is the kind of what the resulting software system looks like. Just a note, you're getting this diagram because I can't actually release all the code. We're going to look at a little bit of it on the screen today. But besides the open source code, I can't actually release it. So what it ends up looking like is a keyword recognizer class that just takes in the WAV file, that makes a prediction, and then it's just, we did an OOP approach. So sorry, object-oriented programming for anybody not familiar. So there's a spectrogram, a CNN, MFCC, and WAV decoder classes that are all part of that keyword recognizer. Daniel's actually going to talk about the how the internals of the model work and all the audio processing.
Hello. All right, so starting with decoding the WAV file. So the way that this was done through the open source TensorFlow implementation was through a fused TensorFlow op. So we never had to deal with that. We just pass in the WAV file, then you get an array of 16,000 floats. So for us to be able to do this in C and in Swift, we had to use Apple's audio kit, which is their way of decoding WAV files and dealing with audio. So we get the same thing, array of 16,000 floats. Can I get the next slide, please?
Yeah, I think it's
There you go. Open source. All right, and then so the next step in the pre-processing is that we want to obtain a 2D representation of our data. So we have this 16,000, this array of 16,000 elements because we sampled at a rate of 16 kilohertz. So we have 16,000 samples per second. What we want to do here is we want to get a better idea of how the frequency components of the signal change with respect to time. So what we do is we run windows of our signal as the signal goes on through time, and we pass it through a discrete time Fourier transform. So a DTFT, in this case, if you're not familiar with it, what it does is it can break down a signal into its essential frequency components. So then by taking all these windows and then stacking them vertically, we can obtain a 2D array, essentially a black and white image that shows how the power in each frequency band changes with respect to time through our 1 second sample. Can I get the next slide, please? Thank you. To continue with the pre-processing, we can then pick every stacked 1D array that we have on the spectrogram, and we run it through a filter bank. So I'm actually going to go back and give a little bit of intuition about what's happening at each step. But the big overview is we filter our spectrogram, each array of the spectrogram. We pass it through a log transform, a discrete cosine transform, then we truncate elements. So there's an aspect of dimensionality reduction here, since our spectrogram is pretty big, and we might not always want to compute so much. So just backing up a little bit to get some more intuition, by taking one of those stacked rows and passing it through a filter bank, what we're doing is we are retaining the important amplitudes at each frequency band that is of interest to us and discarding the rest. So the intuition behind the logarithmic transform is that human hearing is based off of a logarithmic scale, so we don't perceive every intensity the same way. It's linearly, we perceive it logarithmically. So we do a log transform. The discrete transform, the discrete cosine transform, is a bit of an analog to PCA. So if you guys are familiar with principal component analysis, what the DCT is designed to do is to be a computationally efficient way of finding an approximation to PCA. So in this manner, by running this through PCA, through DCT, we can obtain basically the most important vectors. Like you can imagine them being propagating to like the front of the matrix, basically the way that the principal components do in PCA. So then we can just truncate the tail and keep the most important elements. So in this manner, we did dimensionality reduction and got some of the most important pieces of our signal, and then we can pass this into the CNN. So the CNN, yeah. Sorry, could you say that again a little bit louder? Good question. So what he's asking is how much is the compression? So John, maybe you can help chime in on this. I don't remember the exact numbers, but we had basically however many samples were in the window. So if our time series data was 16,000 samples, and then we windowed it, so say we made like 100 windows, so there's like 160 samples. After running it through this entire process, we might have like 13 columns. So that's about, does that answer your question about the magnitude? Okay.
Yeah, so sorry to add on to that. So each window, when we're grabbing the overlapping windows, each window is actually 480 elements. When you're doing the FFT, you have to round up to the nearest power of 2. So that gets rounded up to 512, and then it gets actually cut in half. There's a whole lot of reasons for that that maybe are beyond the scope. But so you end up with 256. And so for an array of 16,000 floats, that spectrogram ends up being 256 by 98, I think. And then the MFCC ends up being 98 by, what did we cut it to? 16, I think?
13 melvins.
Something, yeah, 13, 16, something like that. Something small. Yeah.
Yeah, so you can essentially compress that image a lot is what we're trying to say. So as far as the CNN goes, so the CNN comes from the TensorFlow implementation, so we have a link to the blog post. In the code that they had a couple of architectures that were pretty interesting, so we just chose one to suit our needs. Then we got that graph, and that's what we used to turn into CoreML. So I'm going to have John go ahead and explain that process and some of the tools that he used to be able to make this happen.
Yeah, and so just to show you guys the blog post, this is the one that we're talking about where the training code came from. So if you go to, it's actually relatively extensive. So I think if you go down the how does this model work, it has. Oh man, that's really sad. Okay. Okay, that's unfortunate because I was going to show you guys a lot of stuff in the browser. Hold on one second. Let me see if we can fix this. Sorry, I stepped on it. So I won't step on it again. But so this is the blog post. So yeah, if you go down to how does the model work, there's a couple different architectures here. It explains some of what we just talked about also. And then I believe customizing the model has the different. I believe there's 3 different architectures that came with it. So we just chose the one that was fit our needs the best. But you can explore. There's links to the papers and everything there. But we didn't want to go into that too much since we didn't spend a whole lot of time making those choices ourselves. We kind of took it as a given and chose one that seemed appropriate and moved on. So, so some of the things we had to do were handling the TensorFlow graph. Turned out to be quite a pain. This Metron tool is actually really neat. I don't know if anybody's seen it before, but so it's actually a visualization tool that's used on frozen neural network files. You can download it with pip, and I've used it with Onyx, PyTorch, TensorFlow, and CoreML models. So it renders, depending on how you install it, it either pops up a window like this with a visual representation of the network, and you can mouse over all the different nodes, and it'll tell you what attributes they have. Or if you install it in a different way, it'll render it all on localhost, and you get the same thing. But so that's a pretty neat tool that we ended up using. As part of the conversion process, you need to know the names of all the nodes, and so TensorFlow. I don't know if you guys have worked with TensorFlow, you know this. It attaches colons and zeros and ones and slashes and all kinds of stuff to your node names sometimes. So, actually getting this little graph inspection script working took quite a while, but it turned out to be pretty short. So just loading the frozen graph and then just printing out all the nodes to the terminal was pretty useful. And it was just the magic was just trying to figure out all this stuff, figuring out how TensorFlow deals with the graph def versus the graph versus all this other. Did I lose it again? Oh, I'll zoom in. Sure. There we go. Yeah, just figuring out all this complicated TensorFlow syntax was the fun part. But and then the rest of it's just printing out for operation and graph.get operations, or whatever. But you need those later. Then the other cool thing that I found was actually splitting up the TensorFlow graph required TensorFlow's graph transform tool, which had also a learning curve, but turned out to be worthwhile. You actually have to build the TensorFlow source to use this, but it's relatively powerful. You can slice up the graphs in any way you want. You can get rid of batch norms and drop out layers. You can change to 8-bit calculations for deployment on chips, stuff like that. So it looks something like this. Basically, you have to run it with Bazel, which is why you have to build it from source. So you get some sort of you get an in graph, out graph, the input and outputs you want, and then the transforms you want. There's a whole huge long list of transforms to sort through and figure out the syntax for. And so this is what we use to actually chop the CNN part out of the graph. But this is actually part of the TensorFlow source again. So that was a pretty cool tool that I had to use. So then some of the other tools were the conversion process. We use this TF CoreML library. I wrote a little converter, and then we had to test the conversion and make the CoreML wrapper. So one by one, the TF CoreML was pretty simple to use. I didn't have any problems installing it. Basically just followed the instructions, and there's a notebook full of examples for some common library or some common networks like I think VGG and AlexNet. But it's just about this simple. So I don't know if can you guys see that? So that's about what my code looks like. I can show you. But my code looks just like the second one. Input name, output name, and you need the input shape. So that was why we had to go through this inspection process first. So yeah, this was the converter that I used. So it was pretty much just like the example. Worked great. I guess this is a dead example. So another thing with the conversion process is all these different converters between the neural network formats. You'll find countless issues on GitHub of people complaining about the conversion process not working. I'm getting different outputs now. So it's a good idea to test the conversion. Luckily, Apple has this CoreML Tools library that allows you to run CoreML models from Python. It's the only way I know of to run CoreML models without writing Swift code. I had quite a time getting this installed. I had to reference multiple issues in a specific order. If anybody is interested, I can dig up which ones they were. But once you get it installed, then you can use it to make predictions with the CoreML model from within Python, which I use Python's unit test library, which I know a lot of people don't like, and I know there's better options, but I just needed a couple tests. I believe there's only one here. So basically, just this is the test class. Sets up the test suite. I have a wrapper for the TensorFlow model, and then I just load the CoreML model, and you just have to use an interesting format. So it's predict, and you have to give it. It actually takes a dictionary. So just figuring out the weird syntax. Oh. Thanks. Yeah, so just figuring out the weird syntax, it works great. So these are floats, so this looks kind of weird because you have to do checking equality with floats is not easy. So you have to, go through every element and see if they're within a certain epsilon of each other. But besides the point. The point is you can do this, and you probably should before you go and deploy your model. So yeah, that's pretty much the conversion process. CoreML itself gives you an ML model. So the way, as far as I can tell, the way Apple wants you to do this is take this .ml model, drag and drop it into Xcode, and then it auto-generates 3 files for you, which are a wrapper for the input, a wrapper for the output, and a wrapper for the model itself. The syntax is a little odd, so what I've done so far is just create a wrapper for these models. So that's what I have here. It's just public class CNN. So it's literally just a wrapper for this .ml model, and then I just assign the so the auto-generated wrapper for the model itself. I just assign it to a class variable here, and then there's just an initializer. So I've got a couple of helper functions in here to convert the output and input. It's basically just a bunch of convoluted syntax just to take the input in and get the output. I don't know if anybody, is anybody familiar with Swift here? Probably looks like, yeah. So yeah, this is fun to figure out, but now we have a nice predict API. I think the details here are probably kind of boring, but you also have to dig into the auto-generated class to find out like the name of the input, which turns out to be pretty similar to our TensorFlow. And then they also have different, the API for the CoreML stuff is pretty high level, so if you want to get in and deal with the different arrays and numbers, which I wanted to do, so I have a converter, so it outputs ML multi-array, and whatever, there's a whole convoluted process for this that maybe we can save for another time, but needless to say, a wrapper was necessary. Yeah, after that, I think Daniel's going to talk about how we hooked up some of the pre-processing code in C to the Swift code, and that's all. Does anybody have any questions on any of the tools?
Okay, great. So yeah, as we mentioned before, since we had to split up that TensorFlow graph to separate the CNN with the audio processing pipeline, we basically just redid the whole audio processing pipeline in C. The way that we got our C pipeline to interface with our project in Swift inside Xcode was through the use of a bridging header. So I know it sounds kind of complicated, but it's actually really easy. Basically, you just drag and drop your C files into Xcode, and can we? Yeah. Okay, there we go. Yeah, so basically Xcode just asks you, hey, do you want to generate this bridging header? And I don't know if you can see, but we just write in the declarations of our C functions, and then those are automatically exposed to the Swift compiler. So then Swift can just easily call C functions from inside Swift files. So that's how that was done. And now can I get the next slide, please? So yeah, after discussing the interoperability, here is an example of the whole thing in action. So actually deployed inside the Asteroid application. So on the lower left, if you can see under the orange header, that is the keyword recognizer object, which actually contains the entire audio processing pipeline and the CNN.
Sorry.
It's okay.
How do you play the video?
Anyway, it contains the whole pipeline, and what's actually happening is it's then taking from an external microphone, it's taking clips of somebody speaking words. So in the under the blue header, we have basically a text object that just renders what the prediction is, which you can see on the right-hand side in the white letters. So yeah, that's the example of the whole pipeline deployed on the project. So at this time, we'd like to thank you very much for all of your attention, and I think John and I are going to be ready to field some questions if you have them.
Yeah. Sure.
How did you like using Swift, and are you excited for Swift on TensorFlow?
No comment. I know. Well, so Swift is something we've had to learn. Actually, working at Asteroid, so I didn't previously know Swift. It's okay. I like it. I like it more than I did at first. But yeah. It's not my favorite though. But that's okay. It does a good job for what it needs to do. The Swift for TensorFlow, I've heard about it. I don't know any other details. Is there a when is that?
I don't know the specifics. There's a TensorFlow branch in the Swift repository. Check it out.
Okay. Yeah, that's. I think I just saw like a coming soon in the docs or something like that. I haven't seen too much on it.
It's like 60,000 lines of code or something.
That's looking forward to it. Yeah. Yeah. So I know we came out short, so we can answer questions. If there's any other sections, we can go back over in more detail. Yeah.
Where's the training happening? Are you building an application that your customers will then use to train the model, or are you training it for a set of keywords that you supply?
Yeah. So the question is, where is the training? Are the customers doing the training, or are we doing the training? The customers are not doing the training, so it's deployed and frozen in the app. So we do the training ahead of time with TensorFlow. So it's all happening. Basically, we have so this blog post accompanies a whole bunch of code in the TensorFlow source code somewhere, but they don't link to it. There's basically we have and his keywords in Dvorak. So. Basically, there's a whole section of the TensorFlow in the TensorFlow repo that has all the training code, and so we basically have in our repository we have a forked copy of that we've modified.
And what about the training data? Where are you getting that from?
And so the training data comes from the speech commands data set, which I believe was released by Google, but there's a link here.
Google open source.
Yeah, exactly. So yeah, so it's there. Exactly, yeah. So the data set's, it's I think 10 or 12 keywords or something like that, yeah. Yeah.
I'm trying to get a feel for the signal processing side, the relationship between the amount of audio data you're trying to analyze and the CNN, the size of the CNN that is required. Just get a feel for that. Like, I think you were using 1 second with audio, and that's how you built your convolutional network, right? But if you were trying to do this with 2 seconds or 3 seconds, is this linear? And what type of sizes are we looking for, like for the CNN really, for a 1 second stream? Is there any feel you can give us that? I mean, really, I'm trying to size this thing from a hardware perspective, right? If I was to try to do that, the size of the array, the CNN array, relative to the voice, the snippet that you're trying to analyze. Is there any relationship there?
Sorry, so just to make sure I understand your question, so are you asking how would this thing scale if I wanted to make my sample size bigger?
Right.
Okay, interesting.
Or does it get smaller maybe because you've got more data to work with?
Well, so definitely the dimension, the time dimension will definitely increase, right? So you can keep your windows the same size. You can make your windows bigger. So those are all like hyperparameters you can tune. Definitely, if your spectrogram will get bigger because you have to account for all that data. If you run it through this whole pipeline, through all the way up to the MFCC, you can probably still truncate, so choose the most important components. Hopefully the DCT, it's like PCA, like no matter how big it is, you can choose the principal components. The DCT is gonna try to approximate that, so you might even be able to get away with a larger size spectrogram. It's just you're gonna be limited in that calculation, right? Like calculating the DCT is like n squared log n or something, however big your spectrogram is and however long it takes to compute a Fourier transform, which is how the DCT is actually implemented. So if you're looking for like hardware limitations, dealing with bigger sample sizes, that's gonna be a limit. It's just how fast can you really compute an FFT, right? Aside from whether the CNN will be able to do good predictions on data that is longer than 1 second, and you've run it through this whole process and truncated and everything, I'm afraid I can't answer that. But I can definitely speak to the bottlenecks on the hardware side through the signal processing aspect. Does that kind of help provide more insight?
So the CNN ended up with 8 bits. It went from 32-bit elements to 8 bits in the CNN, or is it reduce the size of the
Uh, Yeah, go ahead.
Yeah. So so we didn't actually change the bit size in the CNN, the floating points. No. So we left them as 32 bit floating points. And so basically and also it's for your earlier question, when we said the spectrogram, for instance, was 256 by 98, and then the MFCC was like 13 by 98. That 98 dimension is what's defined by the time. So that would keep increasing with longer. Yeah, keeping everything else the same, but increasing the size of the wave files would keep increasing that linearly. But as you were saying, there are more computational things to consider, and like the Fourier transform, because Fourier transforms aren't linear, stuff like that. But then the resulting the output of the audio processing is what goes into the CNN. So you would go from so say you made it 2 seconds and kept everything else the same. Your CNN input would be 196 by 13 instead of 98 by 13, right? And just for a rough idea, this model on a MacBook, I think inference time was, I think it was less than 100 milliseconds, just under 100 milliseconds. Does that answer? Kind of. Yeah. Well, we had to get it working first, so there could be some potential for optimization there, yeah.
The problem there is that you've got a fixed CNN, a fixed network that you use, so you're not able to scale 2 seconds or a half second or whatever, because you're not sliding anything through there. You're not doing any kind of dynamic time processing. So they've nailed it at 1 second, and you're stuck at 1 second. You're basically treating that end result as being an image that you're
Right, but are you saying that since it's nailed at 1 second, that if I use a 2-second keyword, it's not gonna?
they're losing it. They're taking 1 second.
They don't stream it. Okay.
Well,
There's
yeah.
no way of signal processing
it can be done, of course, but it's a whole different process.
If anybody can't hear, he's correct that in saying that we can't just dynamically take longer segments of time data, but we actually do implement it. It does kind of stream, so it kind of pings every. I believe it's set to like a quarter second, and so it's taking overlapping segments and then averaging the accuracies, and so that it can run in real time. But to change the input and all those parameters that propagate through the model, you would have to retrain. So that can't be done on the fly. And that was, I think, the point.
If I can just add something, depending on the kind of frequencies that you're looking for, it might be possible to downsample the data. So it just depends on your application, but.
So the actual computation cost for doing the capsule is trivial compared to the CNNs, is where the time is being spent probably.
Yeah.
I mean, it's not trivial, but it's not.
Yeah, the CNN's it's a and the CNN is relatively small, but the CNN is where most of the computation is. Yeah.
But is there,
Sorry. No, go ahead. Go ahead. Go ahead. Yeah.
is there like a relation between, for example, the size of your CNN and your your ability to recognize accuracy, right? For example, so and getting it right every time for false rejection rates or acceptance rates and all that nonsense. Is there any correlations there that would drive, for example, you to go instead of a 1 second window, try to do a 2 second window with more elements, or is there a have you looked into that at all?
Yeah. So the question is, have we looked into different time size windows based on computation and accuracy of the CNN, right? And the answer is we haven't really looked into it. The data set is 1 second wave files, so we kind of rolled with that. 1 second is about enough time for somebody to say a word. When you get into 2 seconds, you could start getting extra noise, and you'd have to get into truncating the samples and stuff like that. I guess some people talk slower. I mean, yeah, there's a lot of there's a lot of things you can play with there, but in general, we felt like 1 second was reasonable, and so we kind of went with that for now. But we didn't spend a ton of time on it. The training code as is gives about 90% accuracy. So.
Did you evaluate pre-trained models or off-the-shelf packages? If so, which ones and what were the problems with them?
That's a good question. So did we evaluate off-the-shelf packages, pre-trained models, stuff like that? So there was a search. There were a few pre-trained models that were MIT licensed, but there's a lot of open source like ML projects out there are just really difficult to get to run. So one, for instance, there was no. It took me. It wasn't clear what version of Python they were using. It wasn't clear what version of the libraries they were using. So it was in PyTorch, and PyTorch updates their API like pretty drastically every single version. So then it was like, and then so I'm stuck emailing this guy, hey, what version of PyTorch are you using, right? And so there was a couple things like that, and then it was like, let's just. We came across this TensorFlow post, and we're like, let's use this. This is robust. There's a lot of code here. Then we kind of don't have to worry about the training process. Then our big concern was just replicating their pre-processing in C and Swift. And then another thing to add is that we wanted to do a lot of it in C. Also, for future expansion and cross-platform stuff. Now we have all the guts of it is in C, and so we can move that to different platforms. And then the CNN, we can there's conversion tools out there, so you can change that around. Yeah. That's all. Did that answer your question? Okay.
Can I add to that?
Sure.
I've experienced that machine learning training models can be very fragile. And that's actually one of the challenges of using them in production is you have to make them robust. So there was an online course that I did when I was learning about machine learning. And the lecturer, he was a Google researcher, posted all the code for the course in a GitHub, and I was able to download it and recreate
I just want to add, I've tried to reproduce a lot of code from a lot of GitHubs, and it's not fun. Any other questions? Oh, sorry.
Do you have some external constraint that made you do it in neural networks?
So the question is there a constraint that forces us to use neural networks? The answer is no, not really.
Because you could probably do a lot higher precision with a lot less computation with a standard off-the-shelf package like Salty.
Yeah, so I'm not familiar with that package. There are a lot of packages out there. I mean, one of our constraints was we're using this for a commercial purpose, so then we have to. Oh, it's MIT. That's good enough. We can talk about it later. Tell me about it.
Were you concerned that you're using different preprocessing tools for the training and inference?
Yeah, so were you concerned that, sorry, just to repeat the question, were we concerned about using different tools for preprocessing and inference? And, and we were concerned ahead of time, but maybe not as concerned as we should have been. It turned out to be quite fun to try and get those to match up. So we were able to replicate it exactly, but it took quite a bit of utility scripts of writing out results to text files and stuff like that to check between the two. So that was definitely the least fun part of this project. But yeah, the one reason we started on that road ahead of time was that the Python code is open source. So it's not so it shouldn't be impossible. It turned out to be quite a pain, but not impossible. I don't know, do you have anything to add on?
Yeah, no, basically that's the reason why we talked about the unit tests a little bit in Swift. We actually did the same thing in Python, and half my library is just unit testing in C to make sure that we can reproduce the same things that the Python TensorFlow pipeline was producing. So yeah, testing is a big thing. Took a big chunk of our time.
Yeah, there was a lot of tests written for this, and there's a whole folder full of utilities for grabbing the model at different nodes and writing out the outputs and automatically comparing them and stuff like that. So it was a lot of fun. Yeah, the question was why did we write anything in C at all, which is a good question. Daniel had to write most of the C code, so I'll let him answer that.
Sure. Well, one of the reasons was that this had to be deployed on iOS devices, so we couldn't deploy any TensorFlow code or anything like that. It had to be in Swift, and we later found out that we could do some sort of interoperability with C. So as far as like dealing with all these computations and things like that, I myself I'm okay in C. So I was able to do this rather quickly, and then we set up the unit test pipeline, and we were able to more or less pretty easily integrate it into Swift. So we decided to just go with that route for that reason. Another reason was that portability across different platforms. So we might be thinking of expanding this to other platforms that aren't iOS. So having this code base already in C makes it pretty portable to other platforms. So it's just something to think about. Maybe we want to deploy this in an embedded platform in the future. So we had some discussions about it, and we decided that just having this modular signal processing library in C was the way to go for this project for posterity.
Yeah.
Would I be able to do that same project in Python, but within iOS? Or no, is it just run better with C, or is it?
Yeah. So and so the question is could you do it in Python? And so you can actually take this project, export it in TensorFlow Lite, but that was we ruled that out. We didn't want to rely on TensorFlow Lite as a dependency. So that was the reasoning behind that. But you could technically take this project out of the box and export it. And I believe there's even code in there to dump that project into an Android project. I believe. I don't know if there's code for iOS, but it should be possible. I believe TensorFlow Lite supports exporting to iOS. I don't know if does anybody else know? I'm pretty sure it does, but yeah. In general, I would it would be a lot easier to do in Python.
So earlier you mentioned you had a time constraint. What was your time constraint? How long did it take you to build this from
The question is, what was our time constraint? Since I mentioned it, let's see. So part of the time constraint for this, so our company has a we have a Kickstarter that we just launched today, where we're selling hardware peripherals to it's kind of like a dev kit. So we want people to experiment with some of these things, and so this was one of a number of things that needed to be done for this Kickstarter campaign. So I guess we went a little bit over time, but so all in all, I think it took. I was working on it by myself for probably about 6 weeks, and then but on a part-time basis, and then Daniel and I worked on it full-time for another 2 or 3 weeks, and then it took another week to integrate it in to the pre-existing system. So probably like I'd say if you add it all together into the same units, probably would take the two of us a month full-time. Maybe 5 weeks, something like that. If you add it all up, right? Yeah.
There were a lot of unknown unknowns while we were doing it. So and
Yeah.
Follow-up question, how's the Kickstarter going? Where can we find out more information?
Sure. Yeah. So I can post a link on the slides here. It just launched today. I think we sold a couple kits. I think there's a couple options, but comes with like we gotta make a brain-computer interface, and there's like some that uses EEG data, and then there's a couple little hardware peripherals, like there's a linear scrubber, like the MacBook Pro toolbar, some stuff like that. I think it comes with a couple microcontrollers too, Raspberry Pi and stuff like that. So we can post a link for it. Yeah. Any other questions? Thanks for putting up with us.
Hey, thanks guys. Thanks guys for presenting at the last minute. You made us look good. If you're new here, if we haven't met, just know that we typically meet. We go from here to across the street to CU29. We'll stay with that routine. Look forward to seeing you, and we'll see you next time.